in this particular topic, this particular engineered bamboo or even bamboo is a very new topic for us. So this is in fact the first time our school we are working in engineered bamboo. So our presentation, this kind presentation and the following presentation, in this first workshop, we are going to present, of course, the research background, why we are doing it, and then the state of the art review. And the workshop in the number 2, which will be in July, we expect to present more of our own results, because then we'll have more data. So just a disclaimer, all the work that we show today, and I will refer to the particular papers that we are referring to, but all the work that we show today, they are all from state of the art review, so from published literature and not by us. So this is the typical timber house frames, and the two, because we are doing it for the first time, and this UGPN project is just for 1 year. We want it to be very focused, and to be focused, we only identify 2 sections for further research or plan for further research. So this the starts are 90 millimeter by 45 millimeter cross section. They are spaced at about 450 millimeter, and so that's mainly structural pine, treated pine, and there would be one of the very commonly used timber products in Australia, in especially residential housing, and we would be looking to replace them with engineered bamboo. Also, another is this deep beams for the floor, which is mainly currently made from laminated veneer lumber, very, very close to the laminated veneer bamboo. Or so LVL and engineered bamboo beams are essentially very, very close to each other in terms of the way they're manufactured. And their dimension usually is 240 by 45, but that varies. It varies from 120 by 45 to 240 by 45. And the reason we are not very worried about the weather effect, so that means the humidity or other impact in this particular part of our research, is because all the residential houses currently being built in Australia are protected, made weather tight by law, using a very good set of weather tight products, and by Proclima or similar companies. So that means essentially not even water vapor can actually reach these within the design period. Ideally, I mean, that's the ideal scenario, unless there is a damage. So that means the frames would be internal frames, so they will be quite free from any weather effect. So that's why we are not looking at weather effect in this particular study. Now, the LVL engineered timber, this is our direct competition, primary competition, and they are also laminated veneer lumber is an engineered wood product that uses multiple layers of thin wood assembled with adhesive. So it very much seems like the engineered bamboo as well. Just they are made from thin wood here, whereas engineered bamboo is made from treated bamboo. Made in factory under control specification, it's stronger, straighter, and more uniform compared to natural timber. And due to composite nature, it is much less likely than conventional lumber to warp, twist, bow, or shrink. So this LVL is what we have to show that we are better than the engineered bamboo that I mean, in order to be convince the construction industry. But there is one reason why engineered bamboo holds an edge, and that's at the end of the day, LVL still needs wood to make it, right? So the wood takes to 50 to 60 years, or at least 20 years or more to mature, most of the cases, where bamboo takes only 3 to 6 years. So that means at the end, overall supply, when we consider the supply, of course, engineered bamboo has an advantage over engineered timber. And this is just to show the kind of price point we have to compete against. Engineered bamboo has to compete against. So the structural pine section that I mentioned, 90 by 45, that's $8.5 per Australian dollar per 1 meter. And the LVL, that's 240 by 45, is about 103 per 3 meters. So that's the price point which one of my students, a summer scholarship student, is working on to come up with a feasibility study. But again, the result is not here. We will report it in our second workshop. So this is the engineer. So the objective of this particular research is to select a range of traditional timber-based construction product with uses equivalent to engineered bamboo. And that's the LVL and the other beam that we have decided. And then evaluate the structural performance and failure modes of engineered beams and lumbers, and identify the test. And so this is a new, or you can say more latest objective that we have added on, which is we are going to look at critical connections for engineered bamboo in residential construction. Our Sao Paulo University partners, they are looking at connections as well, but their connection is for a spatial structure, whereas we are looking at connections for residential housing. So there are two different type of connection approaches. So it shouldn't be any overlap, hopefully. And the type of bamboo that we are looking at are two types of bamboo. One is the Moso bamboo, another is the D-Aspar bamboo. Now, both of them, these bamboos actually can be found in Australia, although they are not endemic in Australia, but they have been planted for some time now, although more like a grove or decorative purposes rather than as a something to use for bamboo manufacturing. But both of these can be found in Australia. So that means it is feasible eventually, if it makes economic sense, to manufacture these products directly in Australia as well. And you can see on the left the hardness ranking, the Janka hardness ranking. This is for Moso bamboo. It's much harder compared to Brazilian walnut, hickory, or even pine. You can see the standard pine that we use in Australia very commonly is only 870 pound force, whereas solid strand oven bamboo, the engineered bamboo, can have almost 6 times the capacity. And this is technical data sheet from Moso Bamboo, and this is a Netherlands-based company, Moso Bamboo, and we are partnering with them to collect, hopefully, and source some of their this particular material, which is the N-Infinity indoor beams, and we have found their data to be most complete in a way. So they have actually shown here that the modulus of elasticity is close to 10, which is the MGP 10 grade pine that we mostly use in Australian standards. So that means they are readily replaceable. They can readily replace the Australian timber, the structural pine. The bending strength value are there, and this company have already produced full life cycle report, which I will refer to later in my presentation on life cycle analysis as well. And then there are many benefits that we already discussed. They have mentioned that on their website as well. So I have referred there. Please have a look on their website for more information. However, so that's one of the Moso-based bamboo that we'll be testing. But the second is, of course, from Bambuilt. And what we have found that in Australia in 2014, we have already at the University of Sydney, there was a research on making low technology engineered bamboo from D-Aspar, and they investigated 7 types of species of bamboo, and from there they identified D-Aspar for the bamboo sample because it was found to have superior mechanical properties over other species and could be splitted easily with simple tools. Because as I mentioned, we are looking at this particular research, we're looking for simpler method to make engineered bamboo. And the comb walls of Aspar was found to be relatively thinner compared to other species, so resulting in lower wastage. So, and what they found was they used 2 different type of adhesive, Parbond and PVA, and they found the modulus of rupture. MOR is modulus of rupture, is essentially your rupture stiffness, and they found to be quite high. You can compare against this one here. This is in megapascal essentially, so 9.9. So if you convert to gigapascal, it's 9.7. Whereas the modulus of elasticity for diaspora bamboo based engineered bamboo, and they're low tech, so not the densification really didn't happen much. So you can still see diaspora bamboo has a higher modulus of elasticity compared to Moso bamboo. So we are very fortunate to be able to work with Bambuild to source some of their beams, and hopefully we'll receive some of these beams which will be in the dimension of 90 by 45 millimeter, and we intend to test both the Moso bamboo as well as the diaspora bamboo and see and report how does each behave. So now I'll move to because as I mentioned, all our work is state-of-the-art review, right? So not our work. So what we have also found or identified are the applicable standards that govern the use of engineered bamboo. And we can see the codes, they're kind of legal documents you have to follow if you use engineered bamboo or anything like bamboo in your construction. They are quite common in Colombia, China, Ecuador, India, or Peru, but no other country have them in codified manner. But we have standards that suggest how you can use engineered bamboo. And the international one is the most common, and they are ISO 22157 one bamboo. Actually, this version has been replaced by 2021. So there is a very recent standard from ISO, which was not reported by this paper mediator. So this paper I highlighted and helped us to identify which particular standard to use for the tests that we're going to do. In USA, the first major code was the ASTM D5456, was first to recognize the laminated veneer bamboo, which is the engineered bamboo beam that we'll be testing as a structural product and provide guidance on manufacturing standard and test methods. And the two other ISO codes are there. So 22157 and 22156, both in some way matter, but for the testing, we'll be following 22157. If we want to use it in structural design, make a structure, make a house with it, we'll have to follow this 22156. Now, in Australia, code wise, we'll have to so we'll follow both, or we'll try to make sure that we also satisfy Australian standard as well, in addition to the ISO standard. So the 4-point bending test that is used to get flexural capacity has this dimension. I'll not go into too much into detail, but it says for the full length, for the dimension of this different end length and so on. This also shows from there, once you do the test, how you get your modulus of elasticity, bending strength, and all other. So we have already identified those, and those who are interested to do more research or know a bit more about it, we are very happy to share this information with you. And this is the tension tests. And then, of course, we have compression test parallel to grain, and then beam shear strength. So all this, this particular code is for timber, engineered timber, which can be used for engineered bamboo as well. And these are some real life experimental photos, again, not by us, but that we found in literature. And then, so this left one is from tensile strength test. The right one is the compressive test on bamboo gum and compressive test on bamboo shimber. And then in Australia, in 2014, the paper that we referred to, where they made their own engineered bamboo from diaspora bamboo species, they actually also did the 4-point bending test here, shown here, and the main two types of failure were the shear splitting under 4-point bending test here, that's the parallel to grain, and then we had tensile failure also at the end. So these are the two failure modes that we can expect in engineered bamboo, and we'll have to get the capacity, and whichever is the lowest, we'll have to take that. And also, this is not 4-point bending, so this is a tension test, and we can see the laminated bamboo actually behaves slightly less stiff compared to the bamboo shimber. And this is what we combined from different publications on different type of bamboo products. So we got in literature, so we have found different, we can see wide range of shear stress capacity, tensile stress capacity, but most commonly, most of the papers provided the compression capacity and some modulus of elasticity and modulus of rupture as well. And we, so again, we will be using that to kind of correlate compared to what we will be testing. And so most of them are not, I think there are Moso bamboo here, but not Diaspora bamboo. Again, just as a comparison, what kind of capacity we're looking at. So these tests all show 15, 16, 14 megapascal. We're looking at modulus of elasticity of 9.1 to 13.7, which is very close to what we can see for infinity indoor beams from Moso bamboo. So now that was the initial test that we have to do, or we will do based following this and comparing this published work. But we want, as I mentioned in our third objective, we want to focus on connections and for residential construction. And for residential construction, which is not under that kind of load, so we don't need bolted connection. We only are after screw connection like this. So these are quite large screws which have a shank without any thread and then a thread component. And this is from Simpson Strong Tie, but there are other providers also. What happens is we need to have usually if you are drilling a large hole, you would have a guide hole and then you put in your screw. Otherwise, the screw can go anywhere. It will be very hard to drill it exactly through. So you can see these are two sections of these are 90 millimeter by 45 sections, and then that's another stop section. So the connection here is that parallel to it is cutting through in grain from these two studs or these two beams, and then is going parallel to grain for this stud. So there is a change in the way the connection occurs. So it will be very interesting for us to know whether engineered bamboo, which is very strong in a parallel grain direction, but not as strong in the perpendicular to grain direction, how does it behave, and whether it splits or whether there are any other type of failure mechanism that happens. And in normal timber, the type of failure that we get and the similar, we expect something similar in engineered bamboo as well. You can see that we can either have a shear plug in bleached. So this is a bamboo, again, engineered bamboo type study as well, so from Hong et al. In 2020. So you can either have a crack directly there or a crack on the edge of your bolt hole or screw hole, or it can just cut through, shear out the whole section. So there are different ways it can fail. And this paper, Urita and Cabrero, the review paper, they kind of summarize the different type of failures that can happen in screw connection in timber. So one is the embedment. Now this left A1 is A version, the embedment. That's the only ductile failure. So that means it gives you some residual load carrying capacity for a certain time out of these four. The others are very brittle. So this just suddenly failed. So they are very dangerous and we need to avoid them all and at all cost and make sure their capacity, our load demand is much lower than these capacities. So it can either split, especially if you have multiple screws, there's a very good chance that it could split, or it could row shear. So it's a shear out type, so you can just cut out from there, or it could be a net section. So, and again, they are different in whether you are considering parallel to grain and perpendicular to grain. And so this is something we'll be looking at in our test when we receive the bamboo products. And these are different type of possible screw connections. So you can either have this type of connection, or it's a double shear, single shear, or you have thin sections on two sides, or relatively similar type section, thicker sections there. So it depends on whole thickness of your timber member, what section you are connecting it to. And this paper, again, very good for us that kind of combine all the timber related research, especially on screw connections, which we will use to compare engineered bamboo against. And there are different failure modes in bolted connection, although in particular, our research will not be looking at bolted connection. But if anyone attending here wants to look into bolted connection, feel free to look at this particular paper on Hong et al. They have very good information or review information on bolted connections. And bolted connection will be much stronger, especially the bamboo thicknesses that we're looking at as quite stronger, and it can have steel plates there as well. And especially this type of connection is more for larger structure or it is possible to have in residential construction, but in our project, in this short term, we are not looking at this. But again, if any of you are interested who are joined here, please feel free to look at the paper by Hong et al. And so there are different type of connections that you can occur. Mostly they involve having steel connections there. So I'll quickly wrap up this part because I need to move into the next part as well, and I will take a break to take questions if any. So there, I think this is a picture that you will see from our University of Sao Paulo as well. So these are this lattice structure or spatial structure that they are looking at, these particular connections are looking at. So again, we are not focusing on this type of connection, but if you're interested, you can look at this paper for more information. And so as I mentioned, most of these cases, it will require a steel component for making these connections work. And this is something we intend to look at some point, but not at this stage. And finally, we have also identified a good paper which kind of summarized all for our case, particularly the screw connection, all the design equations or existing design models for screw connection, especially in the parallel to grain, but we can easily replicate them or calibrate them for perpendicular to grain approach as well. What I just wanted to show here, I'll not go into detail for the sake of time, but they are proposing that we compare three types of failure: splitting failure, row shear failure, and net section failure. That is shown here. Splitting, row shear, and net section, because embedment is a bearing type failure, more ductile, so they're not worried about that as much. And then from there, they have proposed the equation for timber element, and what we intend to do is to recalibrate or maybe improve it for engineered bamboo once we do the test. So that's all from me, and these are all the references I used, or some probably not directly referred to, but we used. Thank you. If you have any questions, I'll try to answer them.